Hi, everybody. Good afternoon at Data Science Conference. Today, we're going to cover the gradient processes based on the deep learning processes. So, this book basically covers all the fundamentals and advanced machine learning and deep learning algorithms for implementation, including the reinforcement. So today we're actually going to cover to see like what are the networks and what linear algebra and calculus fundamentals behind the implementation of deep learning algorithm, and then we will also take a look at in Jupyter Lab to see how we can actually implement certain process at back propagation. How can we resolve error computation? So as we all aware, a number of people have advanced in terms of implementing machine learning and learning algorithms like early in the 1990s. And they were very efficient deep learning networks at that time. And in the recent times, as you see, a lot of people have adopted the machine learning and deep learning algorithms for, uh, with a lot of techniques for natural language processing, speech recognition, or neural translation techniques. From the time where we had like, nodes for the neural network, the world has advanced uh, uh, the number of like thousands of processors. We can connect with millions of new for the convolutional neural networks or recurrent neural. We are able to actually perform some computations which we haven't seen in recent times. For example, a supercomputer and you're trying to compute or map a plane or calculate stars in a galaxy, or you're trying to, like a nuclear test or so forth, that you can achieve uh, the deep neural network. So that's where evolution, like in terms of the high precision mathematical calculations, we're talking about like 1018 of floating precision parameters, like that's like 10 billion uh, pointer computation that can happen with the exascale computing. And that's where we are right now. So we are literally uh, 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 on the like evolution of computing algorithm at a scale that not it's going to be a plasma turbulence or it's going to be a, uh accumulation in terms of like we don't have to really bombard the islands in terms of actually performing the test by sending the nuclear missiles, whether we can in today's world, Oak Ridge Library, Livermore Laboratory, number of other laboratories are already conducting nuclear simulation tests so that we can see, uh, trajectory of the particles and see how much impact it's actually going to create without having uh, bombard the island, create the way that other countries involved in the connecting nuclear. But how can we achieve all of these advancement of deep learning algorithms? So let's look at examine like what are all the industries that you can say like retail industry as including all the industrial corporations uh, that have introduced robotics on the floor where they would like to transport some of their stuff from warehouse to another warehouse where they would like to automate some of the industrialization of their production floor. They're able to do that how are they able to achieve all? So that's what we're going to take a look at. Here's our map that goes to actually implement these type of algorithms. And again, uh, maybe state of um, uh, being a uh, beginner in your career, or maybe as an advanced scientist with skills that will leverage for you. Maybe it's fundamental being algebra and calculus, or it's advanced techniques to see how we can with an existing neural network give some amount of precision in terms of implementation. Obviously, like is where you have a number of algorithms you want to apply. Naive Bayes, linear regression, you have logistic regression, and then you have so a number of machines are already there, cluster technology. But again, when it comes to actual implementation of statistics to neural network, is a amount of math and calculus that we need in here, not just a linear algebra. So that's what we're going to take a look at to see how can we activate this across a neural network. So whatever the algorithm what we want to implement, we need still be able to activate the algorithms and either in PyTorch or TensorFlow or a simple Bear number in Python with this. So all of that we can achieve it by implementation of work. So we're going to take a look at that. Basically, the deep learning is a field of which is a branch of artificial intelligence, is a branch of computer science that originated, several years ago. And so as we spoke earlier, the thousands of nodes that we are processing the networks could be from recurrent neural networks or convolutional neural networks. It could be a deep belief neural network. So there is some echo I'm getting on the call. Audio work, right? So now we can enable that. All right, so I think the video is working now. So let me go ahead and share this screen with you. Okay, great. Everything works. So I was just talking about all of the advancements of human evolution in terms of leveraging deep learning and machine learning algorithms. So we're talking about deep learning algorithms that are applied to natural language processing, neural machine translation. So something like, for example, like GPT-3, where we have some mind-boggling numbers in terms of how much information we can actually translate leveraging the GPT-3. And again, we are also talking about machine vision in terms of self-driving vehicles that operate because if you see and look at 1980s, it was all rule-based machine learning and deep learning algorithms where people are able to primarily compute rules, millions of rules hash coded. There's not anything that works like basically for all conditions. It only works for the condition if it's not coded. If there's no condition, it's not going to function. So we have come quite a long way from the rule-based techniques and Bayesian machine learning networks to all the way to advanced recurrent neural networks and convolutional neural networks. So where we are actually able to achieve all of the computations with neural networks with thousands of nodes, and there is no limitation in terms of how much we can process. For example, if you look at giant project that was implemented many years ago, it took literally years and years for them to even come up with a computation to understand to see somebody how much DNA they have, so how many pairs they have. So that's what it took, and they have to apply several computations with classical computers. There wasn't exact computing. There wasn't a lot of supercomputers that are scalable. that can actually perform computations at a level that we all were looking for. So again, coming to the neural networks, especially in '90s, the neural networks came up, and again in 2000s we have deep neural network. That means that we can process thousands and thousands of layers of neural networks, and we're able to produce the outcomes either whether it's for a supervised machine learning or it's for a unsupervised machine learning or if it's for a reinforcement learning. So all of these techniques we can adopt and implement for all sorts of neural networks. So fundamentally, the deep learning framework inspired by the human network architectures of human brain. Again, as we looked at recurrent neural networks and convolutional neural networks, again, we have a whole lot of other stack of statistics. So we can perform the computation of probability in terms of like we have Bayes algorithms, you have Bayesian algorithms, we have logistic regression, we have logistic linear regression, and a lot of clustering algorithms, neighbor algorithms. You have a whole list of all algorithms that are available. And again, coming to deep neural networks, they are completely independent of this type of statistics algorithms. So because there's a lot of math and calculus that goes in terms of computation and see how exactly can achieve. If you're going for reinforcement learning, we're talking about Q learning or deep Q learning. A whole lot of algorithms you can actually are able to compute. So that's what we're going to take a look at to see how we can actually achieve the computation of neural networks with the help of the gradients that are part of the algorithms and see how we can train large scale neural networks like for genomics or bioinformatics or it's like for any other type of industry, retail, or it could be industrial equipment or supply chain management, utilities, energy, chemicals, FDA regulated corporations also implement deep neural networks. So we're going to take a look at how it actually works and something like automatic differentiation, how we can leverage. We're going to take a look at the mechanics of backpropagation algorithms. And, if we're going for PyTorch, we have a number of built-in packages and libraries that are available that you can actually leverage to compute something like a automatic differentiation. We're going to take a look at Python layer NumPy today to see how we can actually calculate all of it without any built-in packages that we can leverage. Uh, so we're going to, for this example, we're not going to talk exascale computing level. We're going to take a look at a simple neural network which has only a single hidden layer in it, and we have an input layer, we have a hidden layer, we also have an output layer for it. So here we're going to take a look at this. If you take a look at this uh, particular neural network, so we have input neural network, we have a hidden layer for it, a single hidden layer, then we have an output layer for it. So and we're also assigning weights for each of the nodes, and these are the neurons that we're seeing here, and we're going to activate these neurons, and then we're also creating a couple of bias nodes to avoid computational overfeeding and underfeeding, perform some calculation in terms of reduction of the error. So that's why we have that. So now we're going to take a look at implementation of a back propagation algorithm. So you can implement that TensorFlow or PyTorch or Python, but in this case, we're gonna implement with Python and then see how actually we can, we're gonna take a look at the math behind this algorithm, and then we'll come back and then we will actually look at the implementation in Python with code in Jupyter Lab, so we can see how it actually works. So here we are, as I told, Z1 and Z2 are the output neurons, and that's exactly where we are computing everything to the output. And so basically, the way that we're going to perform this computation is there's some initial weight and bias for computation, get the total input and the output values. So the purpose of performing the back propagation, the neural network is to optimize the weights assigned to maximize the mapping of the inputs to the output. So we can just assign some weights here. So we'll have to initialize them and randomize them so that these are equal proportionately uh, allocated for each of the neurons. So here we are initializing the weight, allocating some weight for it so that it can be leveraged for activation of a neuron. So let's take a look at net input. So for example, if you're going for the net input as a y, so we're going to take the weight one and multiply the input neuron, then multiply the weight two with the input neuron, and then we also take considerations of bias and the corresponding node for that. Then we're going to compute the net input. So we're going to calculate this weight for this particular algorithm. So we get the net input as 0.3775. And then we're going to go ahead and take a look at the computation of net input y2. So when we take the net input y2, so we're going to take the weight 3 here and then multiply by the earlier neuron and then multiply the weight 4 and net 4 and then we're going to multiply the input neuron and then we also take consideration of bias node, the corresponding multiplied by 1 and then that gives us the net input operator here. So if you take a look at this, so we are taking a weight 3, and then we are multiplying by A1 plus multiplying by weight 4 by A2 plus bias, and by multiplied by 1, and that is our net input is. So basically here what we are computing is from the input neural network to the single hidden layer Y1 and Y2, what's the input for it, right? So that's what we are computing. This is the net input computed for the Y1, this is the net input computed for the Y2. So now we're going to take a look at that to see how we can apply the backpropagation algorithm. So before we apply the backpropagation algorithm, we need to be able to actually apply the, any type of activation function so that we can activate the neuron. So here we are applying the logistic function, activation function. Yeah, so let's take a look at the, so you can also refer to this particular article that I put it up on the Medium. So you can actually see how you can apply activation function. And this is again available for you. It's not something that you have to purchase the full currency. It's open article on the Medium. So this is the logistic activation function I'm talking in the presentation here. So basically, logistic activation function also is known as a sigmoid activation function. So that helps you to activate the neural network code as well as linear transformation is completed in a hidden layer. So how can you perform a nonlinear transformation with an activated function or with a transfer function? So basically, it's 1 by 1 plus the power of I and z, and that's the logistic activation function, or you can also call it as a sigmoid function. So when you apply that, so basically, just take a look at a few of the properties of the sigmoid function. So the sigmoid function ideally helps to actually able to create a range of the real numbers minus infinity to all the way to plus infinity. So that gives you the range of 0 to plus 1. Okay? So when you're going to actually the output of a neural network, that neural network contains a range of 0 to 1 to be within that range. So we're going to take basically anything that has a nonlinear separable conundrum. So the sigmoid function is basically is differentiable, continuous, and monotonical. So we're gonna take the sigmoid derivative function, which is going to be in cell phase, and then we're going to take a look at the integral of the continuous or nonlinear Bell-shaped function. And with this, I'm actually writing in a PyTorch here. So the PyTorch, you have a built-in function for sigmoid. So all you have to call it you have to import the torch, then you have to import the matplotlib pipeline for actually creating a plot for it. Just create the range of your what is the range you want to pass for the torch range. And then you're going to perform a sigmoid activation function. And you're just going to simply apply y equals the torch of sigmoid. X. So the plot you're going to have here is basically um, the numpy x of numpy y of numpy. So I'm just including with the numpy here. And this is how your sigmoid function is based on the range that actually entered on your range here. So that's what the range will be for this particular activation of the neural network. Um, so if you are not intending to actually, you know, not get in a plot, but you simply want to activate the sigmoid function, you can also achieve that. But there's going to be no plot in this case. You can just simply print out the values of your computed sigmoid function. And so that will be a minimum of y and maximum of y, and then will be in PyTorch. So if you're going for, again, Python and you're not actually implementing this in PyTorch, and then you'll actually have to create everything manually because there's no built-in sigmoid function in Python that you can actually arrange it. So you're going to actually have to implement this in NumPy. So you need to create an array, has values you want to have, and you create your own sigmoid function. There's no built-in sigmoid function like the way you have in PyTorch, like short sigmoid. That's not a function you have in the Python. You manually create it, and you say, as we saw this formula, you want to compute this is 1 by 1 plus e to the power of x or e to the power of z if you're simply going for the derivative of z. So that's when you see here. So I'm going for the x. So x is equal to 1 by 1 plus np expression minus. That is what is going to return your sigmoid function value. And you whatever the array you have created for the range of values, you calculate the activated array equal to sigma activated array, and then you simply put out the values, and that's what you're going to get as your output. So, so you can call the sigmoid activation function a logistic function. They're exactly the same. Both are having a nonlinear transformation attribute, and you can also apply logistic regression, any other type of transformation for you to be able to activate the neuron. So that's what we have taken a look at. Now we're going to go back and see how we have actually implemented this here. So computer already the net input y1 and net input y2, both of them. And here is what you want to know is if you are taking an equal derivative of sigma of error total by sigma of weight 1, it's going to be error total by the derivative of output y1 multiplied by the output value of a y1 by the input value of y1 and multiplied by value of y1 by weight of weight here. That was going to give you the total error in your computation. So you can avoid and reduce the error so that you're going to be having more accuracy. So now we're going to apply the logistic function the way we just saw it in the article that you can read, also available at the Medium. So you can simply go into Medium and click on the. You can also put the link for you so you can see this link. Or to get it again, you are not required to get the book, so you can still get it. So let's go here and access this link. So that will help you to be able to go for the computation of how exactly you're going to activate your functions. Okay. To clear, right? So that's what's going to some sort of automatic differentiation functions from calculus. You can actually be able to compute that total error. So that error total can be computed by the summation of your ideal target minus the actual output whole square. So basically, if you want to compute the Z1 and Z2 are your output neurons, as we saw earlier. Z1 and Z2, you recall that. So Z1 and Z2 is what your output here is. So basically, you want to compute your input for the Z2. So compute the input for the Y1 or Y2 from a single hidden layer. And then now we are coming to the computation of net input CPU, so which is going to be taking the other width that we have, which is at W7, multiply the net output you have received from the A1, and then we process the weight 8, and multiply the net output A2, and we add the bias multiplied by 1. So calculate that's what you're going to get. And so if you calculate the net output V2, it's the same three-mark function we just applied. So if you're calculating V2, it's 1 plus E power of net Z2. So that's what you're going to take. The Z2 you already computed here. The V2 we call it because that's what we computed. So you simply substitute that over here and 1 by 1 plus to the power of net Z2. And then you're going to put this value over here, the net output of the Z2 computer. So if you want to know the entire calculation process, you compute the actually the error Z1, then compute the error Z2, then you sum them up, error Z1 and Z2. So that's the error you have in total. So just simply apply the summation of 1 by radial target, and then subtract that from the actual output of Z1 and Z2 neurons. This is for Z1 net output Z1, which is the earlier stage, right? So now we are trying to leverage the values here, and then you can get an error for Z1 and Z2, and you compute the total error of Z1 plus Z2. So for the errors, that's what your total um, output is going to look like. That's your error total network. So now we have this process of activation of neural network. Now we want to see how we can actually apply the back propagation for this. So we want to compute the back propagation by, so how can we basically determine the impact of the rate of change? So that's what's contributing to your total error. So we need to compute the basically the sum of the partial derivative of error total, and the partial derivative of the total error is present as a sigma error total by uh, uh, the, the derivative of error total by derivative of weight 5. So you can actually implement a chain rule here. So when you implement a chain rule, you're going to differentiate a function of a function. So what is the function of a function? So you can represent the function of function as x of f of z of z. So z of z is a function, and then you are further differentiating the f of z of z. So that's the function of a function. So both are functions on their own. Because z is a function and z of z is another function. So that's when you're gonna to compute the function of a function. So mathematical, if you want to percent, so f of z is basically the cosine z value of z of z, d2, and again f of z is a f z of z, the cosine of z. Then you're going to take this value and you apply the cosine here, and then you apply the chain rule with a differentiation of the function, because our primary goal here is to find the derivative of x by derivative of t. So if you're going to substitute that y as a t of t, this is the calculus chain rule. So basically dx by dz is a dx by dy multiplied by dy by dz. So that's the chain rule we're talking about, the function of a function. Let's see that we're going to take a backward pass in terms of computing the back propagation error. So for that, we can represent the total error for the neural network to take derivative of error total by derivative of weight 5. Now, if you apply that chain rule that we just earlier, and take a backward passage, and you get a total derivative of the error divided by the derivative of the weight 5, basically the error total by output of the Z1 multiplied by output of a Z1 by net output of multiplied by net output as Z1 by the weight 5. So if you further derive this, so the calculate is nothing but a field of computing a rate of change. So whatever the change you have with respect to the a variable to another variable, that's the rate of change. That's what you can compute in calculus. That's what we are trying to compute here by taking the error total 1 by 2 target Z1 by output Z1 to the power of 2 plus 1 by 2 target Z2 and output Z2 to the power of 2. So that's when you can actually compute this error total. So this is the error total here, as you can see on the left side. This is the error we are computing here. So basically, so we have covered about uh, the theoretical conceptualization. Now we're going to actually go for the implementation of it. So let's take a look at how we can implement. So again, I'm going to the code, uh, collab, because just checking with you that if you are able to see this. So this is the Python code we are talking about here. Just getting the, just checking if the audio and the video is visible for you guys. So I assume that as nobody has responded with any issues, that you guys are good with this, so we can go for the computation calculation bit. So we can see how we can actually implement this. So this is basically whatever that we have just covered, math behind the activation of neural networks, and then I'm able to apply the neural network back propagation algorithm. So we're going to take a look at here to see how we can actually do that. Again, now I'm implementing this in a bigger Python with NumPy without requiring any built-in packages like you're going to implement in a, for example, you're going to implement in a PyTorch or you're going to implement in a Python or TensorFlow, you have some built-in packages. When it comes to Python, there are no packages. You have to manually perform all the computations from the here. So any issues with the screen so far? Okay. No issues. Okay. So basically, I'm just creating a simple toy data set here. And for the toy data set, I'm creating a variable radius and a gradient, performing the data clustering on it, and create two variables, uh, basically taking that and the cosine of the gradient and reshaping them, and then I concatenate them and apply. So I want to know what's the cluster values that are going to look like here. And then, so basically, I further apply that and compute and pass it to the variables over here. Then we can see that we are returning these values from our computation. And so I'm just creating the clusters at 900 here. And I'm just creating the toy, essentially sort of a toy data set here with clusters, and we're gonna create a plot for it to show how the points look like based on the Troy data set that we just created. It. I'm leveraging a math library, a NumPy library for plots. I'm leveraging the matplot library, and I'm also taking a SkyPy package for any special report for sigmoid. So basically, this is how I created the toy data set. The values I'm calling them as a cluster one and cluster zero. So the cluster one is basically representing the cluster I created over here. This is the cluster one. And then I created another cluster here. That I created for class one, class one. This I created for class zero and class zero. And so I'm taking both of them and returning the values here. The cluster zero is what we have seen the deep blue over here, and the cluster one is. So now I'm going to take basically, so I'm not going to explain that because I just told you how to compute the total error, how to multiply the weight for each of the combination. So here I'm creating basically I'm creating weights as a C1, K1, K2, K2. I'm just assigning some range of values for the I'm just taking some other values for this, and I'm also randomly setting some values for C2. I'm also setting value for K. Any questions at this stage? Okay, so I think we are good. So now I'm going to go for the creation of a method here, which is a forward prop, and then I'm going to basically create this variable and assign the weights, and that give me the vectorized equation. Now, basically, I'm going to give all the variables here, at V1, I'm going to create here, and then I'm going to assign C1 and K1 to it. Then I'm going to take an N2, then apply the C2 and C2 to it. Then I'm going to compute the sigmoid activation function for and so again, what is sigmoid function? Now that it was going to do that, and that is something I'm creating the IP variable here. So then I'm returning the variables values here. So now I'm creating another function here, backprop, that I'm creating a few other variables, and here I already created a function as a forward method. Basic how can we compute that? So I'm creating the x as NQ and W given as a forward prompt with the G and weight. I'm taking Kn, which is 1 by n underscore points, and multiplied with some of the period we just created here. And I'm applying the log function, and then I apply the back. Here is where we saw the chain rule. So for computation of chain rule, we said that dx by dy equals dx by dy multiplied by dx by dy. So that's what I'm trying to compute each of the values here. We're taking the clusters and dividing with the total and multiplying with the divide function with this. And so I'm going to compute each of them here. And then all of my values is over here. And then I'm creating a gradient. And then I'm passing the C1 from the value that I just computed over here, which is the C1 K1, C2 K. Then I want to return the gradients and Kn function for that. So now I'm going to create a 10,000 episodes, and I'm taking the epsilon as one, which is a learning rate for your neural network. So what is that epsilon? How it works? You can refer to my book. I've explained to you what is the learning rate for training a neural network. You get all the information there, and also refer to the blog I've written, so you understand why you have to take a epsilon as one. Taking an initial weight, copy as a weight. You know, we're going for the losses. Open up a loop for the for loop in a range of 10,000 episodes, and then we're going to compute this gradient scale back prop, and I'm going to assign the values I computed above from the forward prop and back prop, and I'm going to take these weights, weight them, and I'm going to multiply the epsilon with the total gradient. And that's what's going to give me the losses up in here with Kn. I'm going to again take a look at the training log for this. I'm going to actually be able to leverage that with my being a scatter plot here. So we can take a look at that. What it's going to look like for visualization. I just created a visualization function, and so here I'm passing the weights and the earlier variables that are computed here, and then I take the base cluster size of 1,000, and I'm computing that here, which is the I'm taking I'm just putting some color coding of how it needs to look like. I'm plotting the scatter plot here, giving the necessary color coding here, and I'm printing out the visualization. It's going to look like this. So this is the visualization of neural network before letting the weight update. So it's not trained yet, so this is the before the weight update. Then this is after the weight update, which is the weight. That was the initial weight, so the assigned weights here. And then, so after the learning weight update, the superimposed visualization of neural networks after the weight update is how it's going to look. So that is basically you are able to visualize the backdrop with a toy data set. You can apply to large scale data sets if you want to, but again, well, it's contingent upon your understanding of neural networks and how we train them, how can we uh, derivative of variables and uh, uh, applications of some sort of automatic differentiation you know to compute. And then I would say compute on paper, just like we compute on presentation here. You get all of your values, right, everything, and then you start coding for it. So you're not going to have any surprises when you're working at it. You know exactly what you've calculated and you can verify here. So now I'm going to here and ask any questions you have. We just have a few more minutes for today. So I'm going to open this for Q&A, and please feel free to ask any questions by sending the question over here. You can also reach out on LinkedIn for any additional questions you may have, but feel free to raise any questions you have. If you need any blogs or articles, or need any references or recommendations, books, I can provide you. Again, it's based on your industry, your background, and your and maybe you're a statistician or you're you're an advanced data scientist. So no matter at what stage of career you are, certainly your questions are welcome so that I can answer. So I'm gonna take a brief pause here so that I can ask that I can help you answer the question. Any questions you might have? Are you able to still see and able to hear me? Any questions? Feel free to ask. I'll be able to answer you. Okay, if data is highly imbalanced, then how can we implement it? Because okay, so primarily, right? So as we have seen, the important thing is about underfitting and overfitting of your labels of the information that you're creating. So basically, you should be able to navigate and you should be able to actually be able to like uh, question in a way that you're going to. So it all so there's a lot of preparation when you actually process this, especially if you're going for large scale data sets. You have to fine tune the data set, label them, or supervise machine learning or deep learning, and then further you go and actually fine tune. So the best way is instead of we working with data that is imbalanced, we should actually try to label it correctly and cleanse it and prepare it in a way so you can properly process information. Because you're going for any industry, you're going for utility, energy industry, or retail, automotive, anywhere, right? So there are a lot of processes involved in the data quality and data governance before we actually start implementing the algorithms. So the whole time it takes to kind of basically impact, get the information and be able to fine tune it, and then we can actually apply it necessary based on how many number of columns we have and what information that we have to process it and so on. So primarily we should have teams that are some teams who are there governing the master data and able to create the data quality and data governance on these information data sets, and then we'll actually apply the algorithm. If you have one class of uh, deep learning on the data set. Yeah, so again, that's what, like, if you're going for reinforcement learning, or we'll have to think through this organizational uh, data governance processes that we have. How can we actually implement that? Are we actually implementing this with, supervised machine learning or machine learning? Are we implementing with reinforcement learning? So that gives us an idea how much of information we can take there and apply for that. Again, if you refer to the book, you will find in the book, okay, for supervised machine learning, these are the algorithms you can apply in the data set. For unsupervised machine learning, these are the type of information you can process for various classes of information, reinforcement learning, so on and so forth. So you can get all of that information for you. Well, I think that's a question that the host. So basically, I think we have covered for today's session. If you have even questions later, also feel free to reach out on LinkedIn and ask the question. So I'm happy to answer all your questions. Again, you might be facing some issue with industrial implementation. You have some questions from algorithms, so you can reach out, and I'll be able to provide that. Yeah. So for tabular data set, right? So yeah, actually there's a PyTorch Tabular. So there's a separate package you have released, so we can apply that. Or you can also take if you are implementing in PyTorch, the Tabular PyTorch package, you can implement that, and I can share you the article for that. And again, if you're going for PyTorch, then you can actually implement the data frames with pandas as a data frame. So you can so yeah, there is advantage, especially if you are computing large scale computations and you want to get high accuracy, then you can go for tabular data sets, or you can also go for either PyTorch or Python based on your organizational implementation approach. You can go for that. So looking for a sample for that, I can share the sample for you on tabular data set with PyTorch, and same thing with pandas data frames. Actually, I posted it on link. You guys can take a look at that. And if you are not able to find it, then or reach out to me and send me a message on LinkedIn. I will share you those articles I've already shared on LinkedIn. Any other questions we have? Yeah, so basically the tabular data sets you leverage if you have computations in terms of a matrix forms of information, right? So if you have a lot of information, that's when you can go for tabular data sets and you can go for that. I will go ahead and share with you all of this. So LinkedIn, you on LinkedIn? Okay, let's take a look at LinkedIn. You can reach out here. So just reach out here, and you can get all the questions where you're not. Yeah, this is the link. Yeah, that's the correct link. All right, so ignore the. Yeah, go for. All right, sounds good. So if there are no, we are good for today, and so please feel free to reach out here. LinkedIn link if you have any questions, and certainly we can connect. Appreciate all of your participation today, and uh, thanks highly for the host of the conference who have provided the opportunity today's presentation here. So connect soon. We'll see you in the upcoming conference.